Hi, and welcome to a video on our section 10.2, which is Calculus of Parametric Curves. And before I introduce what, sort of is the first derivative for parametrics, let's take a look at this line segment that I have drawn over here to the right. Again, I have put bounds on our t so that it is just in fact a segment and not a big line. But let's just say that this line to the right over here is the tangent line, okay? And again, I recognize that it's a segment. I'm just going to copy down its parametric form that would get us that segment. So that would be x equals 2t plus 3 and y equals 3t minus 4. And let's just say that we're going to use our information from the previous section where we did a lot of algebra with the parametrics, and so we eliminated the parameter. And I would like this to end up in slope-intercept form, which is y equals mx plus b. So I'm going to solve the x equation for t here. So subtract 3 and then divide by 2. That way, when I put this into the equation to the right in place of t, I have the ability to already sort of see it in slope-intercept form. Okay, so y would equal 3 times whatever the t is minus 4, and our t we said was x minus 3 over 2. And again, I want to see this in slope-intercept form as much as I can, so I'll go ahead and distribute that 3 in just so you can see these all kind of the separate terms. So y equals 3 halves x minus 9 halves minus the 4. And then I'll combine those like terms. So it should be y equals 3 halves x minus, 9 halves and 8 halves, so minus 17 halves. And if I look at this line in rectangular form or mode here, I can see that it should have a slope of 3 halves, so the rise over run of this line should be positive 3 over 2, so I'm rising 3, run 2, and that seems to be the case. And then negative 17 over 2 is that y-intercept, which is negative 8.5, and that's exactly where that line segment crosses the y-axis. So this seems perfect. Okay, so if this was the equation of my tangent line, let's say, I'm going to just say then the slope of the tangent line from this would be the slope of this line, which is 3 halves. And the other way that we wrote this was we said, well, if the slope of the tangent line is 3 halves, we said that dy dx, or change in y over change in x, was 3 halves. So with keeping these two things in mind, now let's look back over here at our parametric mode. So if I have the equation for x and the equation for y, like I do, I can find both of those derivatives. So I can find derivative of x, but now x is written in terms of t. Remember, x was a function of t and y was a function of t. So this is going to be dx dt, or derivative of x with respect to t. And so it would be 2, because derivative of t with respect to t is 1. And then the constant plus 3 would go to 0. And then I could do the same thing for derivative of y with respect to t. That would be all the same reasons. And then what I could say is, all right, now that I know that, now I can put this all together and say that if I took a look at, what is dy dx, right? Well, dy dx would be the same thing as me saying dy dt over dx dt, because remember, when you multiply by the reciprocal, that would be like me saying dy dt times dt dx. The dt's would divide to 1, so you're left with dy dx, okay? So that's why that kind of works, and we're going to see that it works right here as well, because when I fill this in, dy dt we just found parametrically to be 3, and dx dt we just found parametrically to be that 2. And there's the same 3 halves that I got over here when I converted it to rectangular mode. or Cartesian mode. So I don't have to go through the lengthy process every time of converting everything to, in layman's terms, x's and y's, right, and eliminating that parameter. I can keep it in parametric mode, and as long as I divide accordingly, dy dt, right, divided by dx dt, so long that that denominator or dx dt is not 0, we can find that first derivative value. So let's look at an example here. Let's find dy dx, because again, the slope of a tangent line is not dy dt. The slope of the tangent line will always be dy dx. So that's really, in essence, what I'm asking you to find here is determine the slope of the tangent line for this given value of t. If I was asked to write the equation, which I am, I will also then need the point, right? So we always need a point and a slope. So I can find the slope. That's the first thing I'm going to be asked to do. But I also have to be able to find the point. So that's something that is not necessarily calculus related. It does not depend on the derivative. It depends on the value for t. So if t is pi, x is going to be equivalent to, use the equation that you were given for x, t cosine t. So it's going to be pi times cosine of pi. And so my x value will be pi, cosine of pi is -1. So the x value of my point will be -pi. And then I would just do the same thing to figure out what that y value is. I will substitute in the value of pi. Well, this isn't going to look quite as nice because there was no trig involved. So it literally just is pi squared plus pi. So the point that I'm trying to find here is actually -pi, comma, pi squared plus pi. So when I get ready to write the equation of my tangent line, I need two things. I need the slope of the tangent line, and I need a point. You need to write the slope or the equation of the tangent line and find the slope of a tangent line at a particular point. Here's my point. Now again, that point was calculated from t equals pi. So okay, let's find these derivatives now. So you can find them in the order you see them and just divide them when you are done. And that's something that I recommend, but you can certainly do it how you wish. So I'll find dx dt, and I'm going to find it numerically as soon as I possibly can. So I'm only going to write out one step for dx dt, possibly do a rewrite or two, but I'm not going to get too caught up in all the algebra I can do because I'm trying to head to a numerical value here. So I do need to use product rule for that derivative. Derivative of t is 1. Cosine of t stays the same. And then I'm going to go ahead and put a minus here. Hopefully you're going to see it in a second, but normally product rule would have a plus. Leave t alone, and then the derivative of cosine t is negative. That's why I changed that to a negative. Sine t. And I'm going to go ahead and finish this one out just so I don't get too confused here. dx dt then at t equals pi, right? Because everything is at t equals pi. We'll put pi in. Cosine of pi minus pi times sine of pi. And then I can evaluate this. So dx dt numerically, cosine of pi is -1. Sine of pi is 0. So dx dt is -1. And I hold on to that here for a second so you can box it, highlight it, do whatever. It's not your final answer, but certainly you don't want to lose it. Okay, now let's do the same thing or similar for dy dt. So dy dt, that derivative of y with respect to t will be 2t plus 1. And again, then I have to put my value in. So my derivative of y with respect to t at t equals pi is 2 pi plus 1. It's not going to get any prettier. There's nothing else I can really do to that or that I would choose to. So my slope of my tangent line is dy dx, and that'll tell you the order in which you divide. So it's your dy dt over your dx dt, which was -1. And I do think I'll just distribute that -1. I don't know, you don't have to. But I think it just looks better. So my slope of my tangent line is -2 pi minus 1. So with those two pieces of information, I'm not saying that this tangent line is going to be really neat, so to speak. It's not going to be like y equals 3x plus 7. They're not going to be all rational values, but I'm dealing with pi, so I don't expect it to be if there's not all trig in there. So y minus, I'm just going to use point slope form, the y from my point, pi squared plus pi, make sure that's a quantity, equals m as a quantity, x minus the x from my point, which will turn that into plus pi. Now this certainly could be left. I'm going to write it, I think, a little bit maybe neater. I'm going to distribute the -2 pi minus 1, but I'm going to leave it as 2 pi minus 1 because that is one value. It's just not rational, but I'm going to leave it as a quantity. So I will distribute this negative on the left so I can eventually combine all of those terms to the right. This will be -2 pi minus 1. I'm going to keep the parentheses times x so I can see the slope of my tangent line is still there. But then I will distribute this to that pi. So it'll be -2 pi squared minus pi. Because then when I combine like terms and I add pi squared to both sides, and I add pi, this does get a little bit nicer. I'm not saying it's amazing, but it does get a little bit nicer in terms of how many terms I'm going to have left, because on the right hand side, that negative pi and positive pi will add to 0. So then I will have, sorry, this didn't stay for some reason. So I'll add pi to both sides. So then I'll have y equals this quantity -2 pi minus 1 times my x, and then just minus pi squared. And that would be how I would leave the equation of my tangent line in slope-intercept form. So now this question, this next one is a little bit different. It says find all points on this parametric curve, x equals 2 cosine t, y equals 8 sine t, that have a slope of a tangent line of -1. So what we're telling you in this problem is a little bit different. We're telling you dy dx is -1, and then we're giving you the two equations in parametric form. So I'm going to need to solve for t. And then once you solve for t, it's important, those aren't necessarily the points on the curve, those are just the t values in which they occur. So we'll have to do sort of that behind the scenes calculation. Remember, t is just that calculator because x is a function based on t and y is a function based on t, or an equation. Sometimes they're not always functions. So here we go. So x is 2 cosine t. Move this up a little bit. So dx dt is -2 sine t, and I'll just find dy dt so I'm ready and have it, but dy dt would be 8 cosine t. And so what I have really is, again, dy dx, but that's the dy dt over dx dt, so that would be dy dx is 8 cosine t, my dy dt, over my dx dt, which is -2 sine t. And I want to know, where is this equal to -1? And I'm going to rewrite this as -4 cosine t over sine t. I'll do one thing at a time here. So I don't think you should, multiply both sides by a common denominator and all that kind of a thing. Hopefully we recognize what cosine t over sine t is. That is cotangent of t. And then if I divide both sides by -4, I get positive 1/4 equals cotangent of t. And many people use the parentheses because otherwise you might forget to write your angle when cotangent ends in a t. And then because this is a reciprocal, I can reciprocate the right-hand side of an equation if I reciprocate the left-hand side. So for example, this could be 4/1 instead of 1/4 if I reciprocate cotangent, which would be tangent. So I have to look at where is the tangent of T4. So because this is not necessarily one of those nice angles that we know, right, we're going to figure this out on the calculator. So I can do inverse tangent. I'm in radian mode. It's important that you know that. Of 4. It's a little slow right now, I'm sorry. But this only gives me one answer, and no matter how I look at it, my calculator is only going to give me one of the two answers. So if we remember, all students take calc, I know tangent is positive down here in the third, and it's positive up here in the first. So whatever this reference angle is, it's going to give me in the first quadrant. I need to transition that to the same angle, but in the third quadrant. So they're telling me that theta, or t in this case, is, keep losing it, about 1.325 radians. And if you're concerned and you think, well, I really feel like that's a nice, neat angle that I should know, you can always convert that to radians, to degrees. This is just taking forever to type. So I'm going to do times 180 divided by pi, and that'll convert this to degrees for me. So let's see here. Yep, and exactly what we knew already. It's 75.96 degrees, which that's that first quadrant angle. So all I'm going to say is theta is about, t is about 1.326. Again, this is radians. And the other answer where it's potentially possible would be pi plus 1.326 radians, because that would be that third quadrant triangle. So I can add pi to this answer and see, not to that one, but rather to this 1.3258 one. So I'll push that plus pi. And that should give me my second answer. So 4.467. Okay, now, if they restricted t, then I would only have to find the ones within a certain window. So sometimes what they'll do, because this technically has an infinite amount of answers, is sometimes they'll say, you know, between t is between 0 and pi, for example, or 0 and 2 pi, because they don't want you to keep going around the unit circle again and again and again, right? Now, when you do that, though, it's important to note that you're only going to get the same couple points over and over again if all you're doing is going around the unit circle in this case, because the sine of t and the cosine of t would be repetitive of itself eventually. So let's just say they stop me from 0 to pi, then I would not include the second one. If there was no restriction, then certainly I would include both. So since there wasn't a restriction written on the original, I'll use both, because again, after 2 pi, I will be repetitive. So if that's the case, now find all points on the curve. These are the t values in which they occur. X is 2 cosine t, and y is 8 sine t. Those are my givens. So I just need to put these t values in to figure out approximately where those points are. And so normally they will say round, right, if they want you to round. I can show you how to keep these exact, because this t is also just inverse tangent of 4. So for example, if I had to keep it exact, I could say x is 2 cosine of, t is inverse tangent of 4. And then again, this is that example which I showed before on a previous parametric curve video of trig, of inverse trig. So this does have an exact value here because tangent, inverse tangent of 4 represents some triangle where tangent is 4 over 1, tangent is opposite over adjacent. So this would be square root of 17. And now I'm saying what's the cosine of that angle? So the cosine of this angle would be adjacent over hypotenuse. So it should be 2 over rad 17. That is exact. If you really wanted to say 2 rad 17 over 17 to rationalize the denominator, you can. You certainly don't have to. And then I would do the same thing if I wanted to keep the y value exact. I would say that it's 8 sine of t, and that is inverse tangent of 4. Oops, sine. Sorry, I forgot the trig function. Sine of, now my triangle, same triangle as before. Since tangent is opposite over adjacent, opposite is 4, adjacent's 1. Use your Pythagorean theorem. That's square root of 17. It's the same triangle. So y equals 8 times the sine of this angle. Well, this would be opposite over hypotenuse. So it would be 32 over rad 17. So one of the points, if I wanted to keep it exact, would be 2 over rad 17, comma 32 over rad 17. And again, depending on if they limited you to 0 to pi or not, there's one of them. And then the other one is going to be pi plus tangent, inverse tangent of 4. So that exact would be a little bit trickier to find at this time. So my guess is these are ones where you would be limited not to 4, but to pi. Okay. Now, if it didn't say exact, you could certainly take this 1.326 radians here and say that x equals 2 cosine t, and we know t is 1.326. So I can say 2 cosine. Again, I'm in radian mode. You may want to check that as you're calculating these. 1.326, and then hit enter, and it'll tell me the approximation. And if we do 2 divided by rad 17, those approximations should be very, very close. Again, I rounded 1.326, so they're not going to be exact, but you can see I am accurate to the thousandth place because they both would round to 0.485. All right. Okay, now this next problem I'm going to go through a little bit faster, so you can certainly pause the video and try it as you wish. It's find the equation of the tangents, possibly, to the curve at the given point. Then graph the curve and the tangents, and here's your parametric curve that's given. X equals cosine t plus cosine 2t, and y equals sine t plus sine 2t. And now we're given the point. So here's the difference. If I'm given the point, I'm not given a t value to put in. So once I found my dx dt and dy dt, just the same as we did in example 1 and 2, and I encourage you to do that on your own if you'd like, I have no t value to put in, which means I need to find t. So that's going to take some solving off to the side. And I just start with, let's say, an x value, right? So where does the x value of -1 equal the x equation that I was given? And now here's where some people say, ooh, I don't know, I don't really want to work with the double angle of cosine. Okay, fine. That's one option. You could also say, where is the y value, right, 1, equal to the y parametric curve, sine t plus sine 2t. Now, sometimes both of these solve really nicely. Sometimes one or the other doesn't solve nicely for you. But I think the y in this case is actually going to pose you some problems because sine of 2t is a product. It's 2 sine t cosine t, because hopefully every good trig solver knows that you need same angle and same trig function when at all possible. So I have a double angle and a regular angle, so I converted them all to single angles. Now people try to factor out sine of t, but it equals 1, doesn't equal 0. And if you subtract the 1, now you lost your ability to factor. So although I know some of you like dealing with sine of 2t better, I don't actually think that it solves better in this case. So we're going to stick with that x value. So where does the x value equal -1? So we do have to know the identity for cosine 2t, and I'll just start with the most basic one. It's cosine squared t minus sine squared t, and then you can put it in any trig function that you want. So for example, sine squared t is the same thing using my Pythagorean identity as, oops, I didn't mean to write the plus. Here's a minus in front of there. As 1 minus cosine squared t. So all I did was replace that sine squared t with 1 minus cosine squared t, and I'll distribute the negative as I combine like terms to see if that helps you. So this is going to become a -1 eventually over here. This is a positive cosine squared t plus another cosine squared t is 2 cosine squared t. And I have that 1 cosine t still just hanging out. So what I end up having to deal with, if I set this equal to 0 and add the 1, I think this is very logical to solve because I can factor out a common factor. So I can factor out cosine of t, and I have 2 cosine of t plus 1. So I'm solving multiple equations here. I'm solving where is the cosine of t 0 for this part of the zero product property. In this one I'm solving where is the cosine of t -1/2. And again, these have infinite values. So I need to find the one t value that not only works for x, because remember we started with the x equaling the -1 for my point, but I also need this t value to give me the y value of 1. So I'm just going to check each of these equations or each of these solutions that I find to the equation to see which one also gives me a y value of +1. So for example, if I'm solving where is cosine of t 0, I'm looking at those quadrantal angles of pi over 2, 3 pi over 2, and I will say etc. I found the first two within 0 to 2 pi. Cosine of t equaling -1/2, so where your x is negative, you're in the second and third quadrants. And so if that's a half, or -1/2 really, these are rad 3 over 2. Opposite your rad 3 over 2 is always a 60-degree or pi over 3 angle, but you're in quadrant 2. So you are 2 pi over 3, and you are in quadrant 3, so you are 4 pi over 3. Okay, so now I need to check which t value gives me a y value of 1. So I just start plugging them in. This is that substitution again. So if t, and I'll subtract or erase these when I'm done here. If t is pi over 2, y is sine pi over 2 plus sine 2 times pi over 2. So that would be 1 plus sine of pi is 0, and there it is. But what's important to note is not all of these are going to lead to correct answers. So for example, if t was 3 pi over 2, I'll show you what would have happened. Plug in 3 pi over 2 for your t's into your y equation. Y equals sine 3 pi over 2 plus sine of 2 times 3 pi over 2. Just checking into this y equation here to see which t value would work. So y equals sine of 3 pi over 2 is -1. Sine of 3 pi is 0. I can see that my y value would have been -1. That one's not going to work. This one's not going to work. This one's not going to work. So once you find the one t value that works, you don't have to continue trying them. You found it. Okay? So you know the t value that makes that point happen for that parametric mode. Okay, so I'll get rid of this because this is just computation. You can rewind the video if you need it. Okay, so now I have a t value associated with that. So this is at t equals pi over 2. So I think now you should pause the video, try to write the equation of the tangent line, and then play the video. I'll do it in the meantime as well, and we'll see if we match. Okay, so here's my work. I found dx dt computationally with that t equals pi over 2 value. I found dy dt with that pi over 2 value for t. I got -2 over -1, so my slope of my tangent line is 2. And using the point that they gave me of -1, 1 and writing it in slope-intercept form, I got to a really, really nice equation that will be the equation of that tangent line. I hope you found this video on first derivatives helpful. The next video that will be created for you will be on the second derivatives for parametrics.